Hey everybody, welcome to the Cybernetters Networking 1 course. I'm Andrew Yick, and today we'll be diving into the physical layer. We will be diving deeper into the technologies on the physical layers, their functions, and their processes, and we will go into detail about how data is being transmitted and sent through these technologies. So without further ado, let's get started. In the last video, communication models, which I recommend if you haven't watched it already, so you can get a basic understanding of the OSI model. One of these layers is called the physical layer, which is also known as physical one. So basically, in summary, what it is it's responsible for the transmissions and received of the bit stream from node to node, and is concerned with signaling techniques. And we will talk about these techniques later on in this video. So have you ever went shopping for these internet packages and then you see these packages like 100 Mbps, 500 Mbps, and 1000 Mbps? Well, this is called bandwidth. Basically, it is measured in bits per second, bits also known as BPS, and what bandwidth is the maximum amount of data that can be transferred. And the formula is F max minus F min. So, for example, let's say you bought the 500 package and your friend bought the 100 package. So basically, what this means is your data for your package gets transmitted 5 times faster than your friend who has the 100 package, and it gets transported 5 times slower than yours. And the bandwidth for the digital signal can be infinite. So there's for now 5 common types of transmission modes. So we have serial, which has the ability to transport one bit at a time, and then you have the parallel mode, which allows you to transport multiple bits at a time. You might think, oh, why can't we use parallel mode all the time? Because stereo's just shutting off all but one lane on a highway, but parallel means you can use all of the lanes of the highway to transport stuff. Well, the main problem with that is synchronization, which is it's harder to synchronize all of the bits sending at one time compared to the one bit, and it's easier to synchronize sending that one bit. But some of the synchronous modes there are the synchronous mode, which is the time based, and there's no gap between data. Time based meaning clock based. It uses a internal or external clock to time the data. Asynchronous is also time based, so it's basically synchronous, but the only difference is there's a fixed gap between the data being sent. And then there's the asynchronous, which is signal based but not clock based. So it doesn't have a clock to determine like when the data is being sent, but instead it uses start and stop bits, which we will be getting into very soon. So diving deeper into serial versus parallel, as we mentioned earlier, the main difference between serial and parallel is serial sends one bit at a time and parallel sends multiple bits at a time. Serial can send data over long distances while parallel can send data over short distances. One thing to note is serial is used by LAN and WAN technologies. What that means is when you want to configure a router or a switch, you use stereo mode to console into it when you're configuring it. Also, parallel is limited by electrical signal inferences, like your microwave running, or when it's the shield is not that great for the cable. So, two more modes we'll look at is synchronous and asynchronous. So, synchronous is time based, which means it uses an internal or external clock for synchronization, which means it uses the clock to handle the synchronization for the communication, and timing is maintained regardless of the presence of data. The difference between that and asynchronous mode is asynchronous mode has no timing source to determine when data is sent. So you might wonder, how does asynchronous use what does it use for synchronization? Well, it uses start and stop bits. What start and stop bits are is basically the start bits signals the beginning of the data, and the stop bits signals the end of the data. And it could have 1.5, or two stop bits. As I mentioned before, stop bits indicate the end of the data, so it allows the receiver to properly process the received byte before the next one arrived. And synchronization must be reestablished every cycle. So here are the timing and transmission examples. For serial and synchronous, you got the T carrier and the USB. And then for parallel and synchronous, you got the printers and scanners. For serial and asynchronous, you have the terminal applications, keyboards, and mouse. But for parallel and asynchronous, it is not widely used in networking because of limitations, but it has been revealed for HPC, or high performance computing. So the reasons why it's rare is because there's issues with synchronization. So without a clock signal, managing multiple parallel data lines can become complex, and bits arriving at slightly different times can lead to errors. Communication, as you know, is very important in networking. So the three types of bidirectional communication is simplex, full duplex, and half duplex. So simplex is basically only one way. So person A, or ding A, can only send it to ding B, but it cannot but ding B cannot send back to ding A. So for example, it could be like the radio station where it can broadcast to you, but you cannot send anything back to it. The next one is full duplex, which is a two-way communication, and it can happen simultaneously. So, thing A can send to thing B, and thing B can send to thing A at the same time. So, for example, that could be like a phone call or your Ethernet cable. And then the last one is half duplex, which is also a two-way communication, but the only difference is it only can do it one at a time. So if one person is transmitting, the other person has to wait until that person is finished transmitting, and then the other person can now transmit after the transmission is over. So that could be like a walkie-talkie where one person can talk at a time, but not two people can talk at one time. Many analog systems are still in use, so that means we need to be able to convert digital into analog. So what modulation is converting digital bits into these analog signals, and it can be sent over an analog medium. Demodulation is basically doing the opposite of what modulation does. It converts that analog signal into digital bits. And then what a modem is, you've probably heard of it, but a modem is a device that performs both of these operations, modulation and demodulation. Okay, so in networking, we have AM and FM. So AM is basically amplitude modulation. So what AM does, it changes the amplitude, which means height, of the carrier wave to represent different bits of data. So, for example, it can be used in radio broadcasting because AM waves can travel long distances and they're prone to interference. Now we have frequency modulation, or FM. So what FM does is it changes the frequency, which is the speed of the wave oscillations, to represent data. So FM is more commonly used in digital communications because wireless networking, also known as Wi-Fi, and mobile telecommunications, because it is less susceptible to noise compared to AM. So it is also used in signal processing and modern radio broadcasting and computer networking protocols. So think of FM like a car honking its horn at different speed. A fast horn or half fast honk might represent a 1, and then a slower honk might represent a 0. So, shift keying is when you manipulate a particular characteristic of a carrier signal to encode information. So, the types are ASK, which we talked about, which is modifying the amplitude, FSK, which modifies the frequency, PSK, which modifies the phase, and then QAM, which modifies both the AM and the PM, basically, which we'll be talking about in the next slide. So the graph you see on the right shows the carrier signal, which is a continuous unmodulated sine wave with a constant amplitude and frequency. There's also the digital signal, which represents the binary stream, which binary 1 is known as the high signal, and binary 0 is known as the low signal. And then also, you have the carrier with the amplitude shift keying, which means when a digital signal is 1, the carrier wave shows it as a high amplitude. And then when the digital signal is 0, the carrier wave either has a low amplitude or is completely suppressed. So, as we talked about in the previous slide, quadrature amplitude modulation, also known as QAM, is a digital modulation technique that combines both AM and PM to transmit data effectively. So, by doing so, QAM can transmit multiple bits per symbol, which increases the data rate. So the types of variants we have for QAM is the 4 QAM and 16 QAM, 64 QAM, and 256 QAM. So let's talk about multiplexing and demultiplexing. So basically, multiplexing is when you have multiple senders using one shared medium in order to send to many receivers. So basically, as you can see in the diagram, the senders are like the input sources. You can see sender 1, sender 2, and sender N, which sends independent data streams. And then the multiplexer combines these multiple signals into like one single composite signal for transmission, which is sent over a shared medium, which is probably like one communication channel, like a fiber optic cable, which carries all the combined signals. And then you have the demultiplexer, which receives it and then separates it back for the receivers to receive all the messages that the sender sent. So next, we're going to talk about frequency division multiplexing, or FDM. So imagine a highway. Each lane is like its own like sub-frequency. We can like apply that in FDM. So each input data stream is assigned to like a sub-frequency onto the channel. And what a guard band does is it minimizes adjacent channel interference, which is like the lanes of a highway preventing cars from like going into a different lane. The next type of division multiplexing is time division multiplexing, also known as TDM. So imagine a rotating restaurant where each like table gets a slice of time to look out of the window. So TDM is similar to that where each input stream is assigned a time slot and data can go through that time slot only. Just like how each table gets its own time to see the scenery outside of the window. The last thing we have is code division multiplexing, or CDM. So think of it like as a crowded party where everyone is speaking different languages. Even though many conversations happen at the same time in the same room, each person can focus on their conversation in their own language while ignoring the rest. It's like CDM because multiple signals share the same channel, but each is encoded with a unique code that which allows devices to distinguish between their own data from the others, just like understanding only the language that they know. Thank you so much for watching. If you have made it this far, I truly appreciate your time and attention. If you found this video helpful, don't forget to give it a thumbs up and feel free to subscribe for more content like this. Do you have any questions or feedback? Drop them in the comments. I'd love to hear from you. Until next time, keep learning, stay secure, and I'll see you in the next video. Bye bye.